Okay, so welcome to video one of this course ST2 on hypothesis testing, and today we're going to look at normal distributions and Z testing with R. Note the main part of this part in R will be done in the demonstration video for lab one. That includes Z testing and other aspects of our studio listed below. So remember, for this portion on normal distributions, the theory behind it is that we're trying to take our data, make sense of it by extracting information from it, and we're trying to estimate the uncertainty associated with that information and to better understand the models that we've created and allocate sources of error to different components of those models. So remember as well that we're also trying to tell a story with our data and understand what it means to other collaborators that we might have. So we're mainly going to focus on this situation where we've got appropriate data and then we're trying to build models. Z-test normal distributions is an example of a model. And we might test it and we have to refine our model in some way to further understand what's actually going on. So we can think of this as an iterative stage. So what we're going to think about is that after our experimental design and summarizing the data, we might try to analyze the data using Z-tests or T-tests or that sort of thing. And that might give us some sort of interpretation. We have to think about our model-based thinking for that, rather than thinking of this as using RStudio or something as simply a portal to perform calculations. It can be a portal for modeling, for trying to understand better what we're trying to achieve here. So think about how these different stages flow into each other. And if you haven't heard me mention Li Peng before, this article in Science is very, very useful on what is a data analysis. And what's important to think about is that we want to summarize our data, interpret it ideally to go beyond just description, to explore the data fully, to test whether it holds in a new sample, and then we might be able to typically have some sort of inferential model about what we're discussing. That's usually as far as we will go. There are other types of models as listed here, but they're not ones that you're likely to encounter frequently in your analysis. So we had this picture before in ST1 where we're looking at different types of data, and here we're kind of steering away from the discrete towards the continuous end. So we're kind of heading down here to think about if looking at differences between groups or relationships. Relationships would be some sort of linear model, which we don't have here. We're looking at differences, and we'll be looking at the means and variances of different groups. So we're mainly looking at two groups here rather than more than two. And we're typically assuming that the parametric assumptions are satisfied, but we're going to probe that further as we go along. So you may use things like t-tests, other types of tests, but there are rank-based alternatives available as well if we have non-normal data. There are a lot of different distributions that are out there. The normal distribution is one we're most familiar with. The t-distribution is similar to the normal distribution, but it's a bit wider and has a higher peak. And then there's other distributions, the beta distribution, binomial distribution, chi-square distribution, F distribution, and so on. And they are different models for how our data is distributed. So a normal distribution is just one. So if we look at this diagram of different distributions, we can think about what we understand so far in the courses we've done. And we're kind of sticking to normal distributions or standardized normal distributions. And they're very good for dealing with continuous data. If we're looking at coin tossing or dice rolling, well, coin tossing really, we can look at binomial distributions. And then we have other variations on that kind of link in together that are similar depending on how complex a phenomena we're looking at. We also have multiple variations, and then other distributions we'll talk about later, like chi-square distributions, F distributions, and here we're going to talk about T distributions. We also have other types that we can look at, like we're going to look at uniform distributions in relation to p-values, and then the T distribution, where they're going to be quite different. And then we're going to think about how they fit into the different types of data we might have. So enumerative data, remember, means tabular data or grouped data into groups, numerical groups, not continuous data. Or we're dealing with continuous data like say heights or equivalent here. So we're going to have data that maybe looks like this. And we're going to ask, is this normally distributed or not, as a kind of first check. it kind of has that shape, but we're not, maybe not sure. We also have to counter that we may hypothesize that we have a distribution that looks like this, but in reality, we might get something that's actually quite different. So expected shape for a normal distribution has a particular formula to describe its exact shape. And what's interesting about this distribution is that it is symmetrical on each side and it can be standardized. So when you see N01, that means it's been standardized as a distribution such that the 0 is the mean and 1 is both the standard deviation and the variance, which are set to 1. So we can kind of manipulate distributions to transform them from their original mean and variance to a modified one. And what we can do with this kind of basic information where you have the standard deviation and the mean is we can apply existing knowledge to that whole area. So if we have a distribution shaped kind of like this is my bad normal distribution, and we have mean here, and what we can do is travel one standard deviation away to this point. So that's 1 SD minus 1 SD, and therefore we can calculate what's in this area on either side. So we can go on the other side as well, 1 SD. So let's say that's here in my slightly warped distribution. We will know that about 60% of our data lies in this area between each of these two standard deviations away from the mean. So this is our mean mu. And then if we travel further, we know that if we travel further, one standard deviation further on in my very, very approximate cartoon version of this, that's minus 2 SD. And this dotted line represents plus 2 SD. That in fact corresponds to 95% of this area, and that corresponds to the empirical rule written over there. That if we know the mean and the standard deviation, therefore you can get a sense of how much spread we expect in our data. And furthermore, if you go out to 3 standard deviations, we get the next value here of 99.7, so that's plus 3 here, and then minus 3 over here, and that will give us 99.7% of our values inside this range. And if you go look in further detail, if we assume our data is normally distributed, there's a number of things that we can talk about in terms of how far, how much of our values are contained in different subsections of this area. So you see there we have 0.34 is in here and 0.34 is here in this, going from left to right here from 0 to plus 1 standard deviation. So that's why this point here and this point here together correspond to 0.68% of the variation present. And therefore we can use this distribution to map our percentiles onto it. So we might have kind of a first percentile, maybe somewhere around here. And then this is the median, the 50th percentile here. And then we have our other first percentile somewhere down here, roughly speaking. So this distribution was developed in 1733, first by de Morgan. Kind of came from a binomial distribution that you might be familiar with dice. And Carl Pearson rediscovered this in 1924. De Morgan's initial number distribution was also discovered by Laplace, who thought of it as a spread of errors. And then the Gaussian distribution we're familiar with also looked at it from the shapes we have in astronomical data. And we're also familiar with the term of bell-shaped curve. So normal distributions have been studied for quite some time, and therefore they predict a behavior that can sometimes be useful for describing the data that we encounter. So if we think about z-scores and how they relate to the normal distribution, we have our value for mu and the SD, and we can say a lot about our data with just that. So you can translate our z-score into some data point of interest, x, minus the mean over the standardized value, which is the standard deviation. So if we have a mean of 5, a standard deviation of 2, and we have a new value of 11, we can use this formula above to work out how far this lies on our Z distribution. So that corresponds to where we place our value on this distribution. So we have Z scores going out here from 0 to positive Z scores out here, and 0 to minus Z scores over on this side. So then we can calculate our Z score. So this Z score is +3 because 11 is much bigger than 5. And that means we can give the context how variable that data is, the context of the wider population. And we have another question there. So if what Z value will we get if X is equal to 1 and we have a distribution of 12 plus or minus 3. So then we just use the formula above. So we have 1, oh dear, pen, 1 minus 12 over 3 gives us our value of minus 11 over 3. So this case, our Z score is quite negative. And if we do this distribution, which is usually a good idea, my slow moving pen, so it's not very good. If our mean value is here at 12, then if we've got value here 1, so 1 is going to be somewhere over here. So it's quite far away to the left-hand side. So therefore, this Z score is quite negative here. So if you think of the Z scores as a transform operating across here, where here corresponding to the mean is Z equals 0. Z is negative here, and Z is positive here. If we look at other examples, we have another one where we have X is equal to 17. So we just do the same formula. We have 17 minus our mean 5 over 6 is going to be 12 over 6, which is going to be just 2, Z equals 2. And we know that, therefore, that from a distribution before, that if Z is +2, then that must mean that there's 2.5% of values that are more extreme than this on that side. So we think of it like this. We have a distribution here, we have 17 here. Oh wait, no, we have 5. 5 here. 17 is over here. And we're moving in units of 6. So this is 11 in between. Here, here. If we went to the other side, we go down to -1 at this first standard deviation jump, and then -7 down here. So that kind of gives us our distribution shape. And essentially, we're just transforming the coordinates on the bottom and converting them into Z scores. So this is a Z score of 0. This is a Z score of 1 corresponding to 11. 17 corresponds to Z score of 2. -1 corresponds to Z score of -1 in this case. And -7 corresponds to Z score of -2. So that's our Z distribution. If we have X equals 1, in essence, it's the same distribution, but we're just putting our values somewhere here. So what we're going to do is calculate our Z score corresponding to this point. So it's going to be 1 minus 5 over 6, which is going to be about 0.67. So what we can see there, if Z is positive, then X is greater, or vice versa. And if Z is negative, then X is negative as well. If you look at, yeah, this is the same one. So what the next step then is to calculate this area under the curve if we value here. So it's like what we had here previously. We want to get, this corresponds to the area under the curve that is more extreme out here. And that's the next step. That corresponds to the p-value. In this case, it's a one-tailed p-value because we're only looking at one end of this distribution. If we're looking at both ends, we'd get the symmetrical area on the other side. And that would be two-tailed. by summing the total area in both these kind of red blobs here and here, and that would give us 5%. So that would be the p-value 0.05. So we'd write down 2.5% as 0.025. So then that brings us to our definition of the p-value. And what's very important to note is the p-value is 7 different things associated with it. And we usually we're describing that we have 2 hypotheses, some sort of null hypothesis here, H0, and alternative here, such that the alternative is true if the null is false. And we have some test stat, like our Z stat, whose distribution is known under the null hypothesis. And that's very important. What is a null hypothesis? And is our distribution known? Typically in biology, this is not true, and our null hypothesis may also be misguided. And therefore, what we're looking at is the probability of getting our test, our value of interest, like X, that is as extreme or more extreme if the null is true and if the model is appropriate. And this is very important. Often the model is not actually appropriate, and often the null hypothesis can be poorly designed or poorly considered. So that means the p-value is not the probability that the hypothesis is true or false, and it has no commentary on whether that data is produced by chance or is not chance. And it's really important not to think about this kind of very categorical perspective, where you get some p-value threshold like 0.05, you say this is just random if it's larger than that, and this is, and it's some sort of significant association if it's less than that. That's not true at all. And I'd advise you not to use the word term significant. If you're a biologist trying to understanding what's going on in your system, that's not going to help you in trying to understand. And having such a simplistic interpretation of what p-values are is very much a hindrance. So please avoid this kind of simplistic thinking. But let's go through a few examples of this. So if we have in your lab, you have Minnie the mouse, and the mouse can run 10 meters in 12.4 seconds, and the average time for mice in the lab is 11.6. The standard deviation of 0.4 seconds. You can ask, how fast is Minnie? So Minnie's actually over here on this distribution. The mouse is going to be over here at maybe 12.4 seconds. And our mean is going to be 11.6 here. And that means you can guess already, we can work it out, but I'm sure you can guess already that when we work out this difference, that Z is going to be -2. So that means you can know automatically that roughly the p-value is going to be small and around 0.25. Not exactly, we're going to see that when you actually calculate it with RStudio, you'll find that it's 0.023 to be exact. And that corresponds to the area on the curve over on this side. So that's the area that's more extreme than the value we've seen. So this diagram is not to scale, but it shows that the area is on this side is what we're calculating. So therefore, we can place these steps into some sort of order that we can think about. Firstly, what is our hypothesis? What's our alternative hypothesis? What is our Z stat in this case? What is our p-value? And our interpretation of this at the end. And what you see here is a slightly different formulation of the Z distribution. But here, in theory, if we had all the samples in a population, we could use our value X minus mu over the standard deviation. But here we've taken into account that we have only sampled some of them. So to scale for that, we can adjust for n as the denominator here. And we can look at the deviation of our, in this case, our sample mean away from the population mean, scale by this value. So the different formulation that we'll look at further. There's another example here So you're looking at the response time in rats in seconds. So they established that the normal response time is 1.2 seconds. You got 100 rats with a mean of 1.05 and a standard deviation of 0.05. So you're going to say that the rats are assumed to be the same as normal rats in terms of their response time normally. And the alternative is that they're not. So therefore, we can next get the Z distribution. So that's going to be equal to 1.05 minus 1.2 over our expanded denominator of 0.05 divided by root 100. And then we can work that out that that's going to be approximately 3. So that means we know that we're going to have a small p-value, something, less than 0.01 anyway. And that's the next step to work at the p-value and then interpret the test. And that would suggest that the response time of this sample is different to the existing rats and that they're much faster. That's what we can say. Okay, so we can look at another example where we have a water bath in a lab. And here the water lab is being used for an average of 2 hours per day. And if we have a standard deviation then of 0.2, what's the chance the water bath is being used between 1.8 and 2.75 hours a day? So what we need to do is get the Z value for this one, the Z value for this one, the P value for this one, the P values for this one, and visualize them in distribution like we have below. So for our first Z value, we know will be below the mean, which is kind of this point here. The other one will be greater than the mean of 2 hours, definitely. So that will correspond to this one down here. And therefore what we want is the intervening area. So slightly different here. So this p-value will correspond to the white area initially. So what we want is to get the difference between these p-values in essence. So if we do our first calculation, we'll get 1.8 minus 0.2 over 0.2, which will be minus 1. And then if we do our second calculations, 0.275 minus 2 over 0.2, which is 3.5. So these p-values may not be correct, but you'd expect that 0.35 to be about 0.995 or so. And this one, if it's minus 1, is going to correspond to, we know already, that's going to be 0.32 or thereabouts. So therefore, we can get the difference between those two to get our answer here, which is going to be similar, but it's going to be slightly wider in this case. So it might be 0.675 or something like that. Again, we'll do this with ST2 to get the exact values. So then we can think more carefully about if we do this experiment many, many times. So if we have some population ever mean mu with some variance, and then we have a single random sample that we're performing. But if we take many, many random samplings, we can think about how similar our sample is compared to the population mean as well. And we can repeat this over and over again. And each time we take x1, x2, and so on and so on, if they're independent samples, each of these, its x bar mean, that will approximate our true population mean, but it won't be exactly the same. And if we have a larger sample size, we'll expect that this estimate, this inference of the population mean from a sample mean will be improved. So to scale for that factor, we have our standard error. So the standard error is the standard deviation divided by the square root of n. So that refers to the standard error of the mean. So if you're reporting variation in your data, remember the standard deviation corresponds to that. That's the data variation, spelled poorly. And then the population within your collection. And then the standard error refers to your ability to estimate mu from your sample. So in this vein, you can imagine that if we take one sample, say of 25, and we estimate the population mean from that, and then we continue this process of getting many, many samples like X2, X3, and all these ones here, and gradually do that over and over again, and get many sample mean estimates from the same set of 25, some same sample number of 25. I repeat this many times, will eventually approximate some sort of estimate of the population mean. And what was worth noting is that this approximation will actually be a normal distribution of cells. So when we take a sample, the distribution of sample means is a normal distribution. So this is separate from the distribution of the data itself, which might be normal if you're lucky, but this is separate. So irrespective of the underlying distribution, if it's a uniform distribution, you completely take samples from the uniform distribution of 25 each. Those distribution of sample means will approximate a normal distribution, even though the originating distribution is uniform. They're independent. So you can see that here, if we have a normal distribution and we take more and more samples, we'll find that our estimate of the population mean gets better. And that's where this formula comes from. This is our sample mean, population mean, and this is our standard error. So we can say that for a data set, we have said with the x minus mu over the standard deviation, and that's different from our estimate of the standard error and our sample mean and our population mean. If we had a skewed distribution, we had to see the same thing. The sample distribution would look like this. And same for the uniform distribution, which I just alluded to. As long as we have more samples, we'll find that it approximates a normal distribution with a predictable shape. And that's true even if it is a irregular distribution, because if we still get a mean value somewhere here in the middle and do this over and over again, even though the initial distributions might have a peculiar shape, eventually if we have a large enough sample size of the sample means, we'll find that it has a normal distribution shape. So that's kind of a universality, that we have two separate things: the original distribution of the data, and this is the distribution of the sample means. So in this way, what we can think about, and this is from a points of significance article, that as we get more and more samples, we can see there that our standard error of our mean gets better. So each of these gray, black, and kind of white unfilled lines indicate estimates of the standard error of the mean as you have different sample sizes. So those three independent estimates are very far away from the two values at the start. They're quite different for very few samples. And as we get more and more samples, the standard error becomes more accurate. So if we have something like 30 samples or maybe even 20 samples, we'll have a decent estimate of the standard error. But if we have only 10 samples, it'll be quite poor. For the standard deviation, we can see that if we have 10 samples, it's still very, very wild. It's not realistic. If we have 20, maybe it's better. 30, there's still some variation, but certainly by 50, it's more constrained. So you can see how our estimates of what the true population-wide standard deviation is are quite prone to the sample size. And the same for the sample mean. You can see here at the top, our estimates are very wild early on. Even if we have a sample size of 30, there's a lot of variation here. And then as you get to a sample size of maybe 50 or 60, we get a better estimate, but there's a lot of variation. And that's very, very important to think about. The spread of values that reflect where our true population mean is can be quite wide. So we may have a point estimate from our sample mean, but that estimate may have high level of uncertainty if the standard error is very high. So we can summarize this by saying that we have this formula, Z transformed without the sample size if we know all the samples in the population. But if looking for a set of sample means, the formula is different. And that brings us on to the next step, think about, rather than trying to estimate, get a point estimate every time of the sample mean, which may not be meaningful. We think about confidence intervals and how we can extract those from data using our z-score. So that gives us a range of values on either side. If we've some estimate here for our values, we want to think about a confidence interval going from maybe minus 1.96 to plus 1.96, which would give us a 95% confidence interval. So we can see that represented over here. So if we have our sample mean here, x bar, the error bound for the population mean, which is roughly speaking the confidence interval, and that corresponds to the percentile. If we have alpha, so let's say alpha here is going to be 0.02, so that means we have 1% of our area here, 98% of our area here in purple, and then 1% over here. So think about the z-scores that correspond to that percentile, which is going to be greater than 2. We know that much at least. And they in fact correspond to minus 2.327 and plus 2.327. So that's where they lie on the Z scale. So then we can use these values then to put into our calculation to get answers on what value we expect these correspond to. So what is X here and what is X here in our formula? So if your X bar is 11.6, what we do is then have minus 2.327 is equal to X minus 11.6 over 0.4. And we work this out to estimate X, and we do the same on the other side to get that value on the other side. And that will give an estimate X. In this case, this X corresponds to 12.53 if you work this out. And this one is 10.67, as you can see in the diagram below. This is where they lie for this particular distribution shape. So that's a 98% confidence interval. We can slide the same approach for other confidence intervals, and from 95%, 90% to 99%, we can do that all. So if we go back to our mouse running example, if the average time is 11.6 seconds and the standard deviation is 0.4 seconds, we can get the 90% and 95% and 98% confidence intervals using the formula we had before, and that corresponds to the ones down here. We had the Z formula is the Z value we need is roughly 2.33. And what's important to note is that we need to have this formula here. So if mu, our value plus minus Z plus the standard deviation by the standard deviation. So we know that for the 90% confidence interval, that corresponds to Z going from minus 1.96. So that's our distribution here. So think about minus 1.64 to plus 1.64 with Z equals 0 here in the middle. So getting this area in here, that's what we're looking at. And the same if we're getting 95% into confidence interval, our Z value then is going to be 1.96 instead. And we just put that in there. So it's the same for startup each time, 11.6 plus minus the Z value multiplied by the standard deviation. And you see then for a 90% confidence interval, we would have values that are more narrow, going from 10.9 to 12.2, whereas for 98%, we get a wider confidence interval going from about 10.7 to 12.5. So our estimate is wider there. So that means we can summarize what we are talking about here in simple terms, that a standard deviation refers to the data points given that we have, where the standard error refers to the accuracy of the sample mean compared to the population mean. And therefore, for an infinite population, which is not possible, we can say that 95% of the data lies within 1.96 standard deviations of the population mean. In reality, we're going to deal with a sample set with a mean S in this case. 90% of that data is going to lie within 1.967 by the standard deviation. And then if we have a distribution of means, 95% of the averages are going to be within 1.96 times of the standard error of the population mean. So that concludes this portion on normal distributions. Please see the demonstration video for more details on how to implement this with our studio.